In this video, I'm going to be going through pacemaker action potentials, APs as they occur in the pacemaker cells of the heart. I'm going to be comparing cardiac pacemaker APs with skeletal muscle APs as I did in video 1 of this series, specifically just to give you a sense of similarities and differences. If you need a primer on skeletal muscle APs, go back to video 1. I'm not going to do a full run through skeletal muscle APs here. So let's jump right in. Here's our skeletal muscle action potential. And if we kick it to the background, let's see what happens in the pacemaker cell. We begin with the pacemaker cell drifting towards threshold. Now notice, there really isn't a resting potential. I've not shown the cell at resting potential, and I'm not showing it being stimulated to threshold because there are extra leakage channels for sodium in these pacemaker cells. Extra leakage channels means more sodium can leak in, and it can leak in faster. And the result of that extra sodium leaking into the cell is the membrane really doesn't settle at resting potential. It just constantly drifts towards threshold. When it hits threshold, obviously we've got sodium that can move in, but in addition, we have calcium voltage-gated channels that open at threshold, and the additional influx of calcium combined with the sodium that's leaking pushes the cell into a depolarization phase, and we get something that looks similar to but is slower than skeletal muscle depolarization. After depolarization occurs, potassium voltage-gated channels open, calcium voltage gates close, and the outflux of potassium pushes the cell back towards resting potential, or what we might call resting potential, in its repolarization phase. Now notice repolarization here is much slower because at the same time that we have those potassium channels open to allow it to go through repolarization, there are still leakage channels for sodium open, and so we still have some sodium trickling into the cell and countering the action of the potassium leaving. So it slows down the rate of repolarization. The key here, though, is because of those leakage sodium channels, when the potassium voltage gates close, sodium is still leaking into the cell, so it begins drifting back towards threshold. It doesn't settle at resting potential. It just immediately moves back to threshold. These pacemaker potentials, this drift towards threshold, accounts for the autorhythmicity of these cells. Pacemaker cells don't need the brain to tell them to have APs. They repeatedly have spontaneous action potentials as they simply drift towards threshold. So if we do a final comparison, cardiac cells do not return to resting potential. After one action potential, they just drift towards threshold again. The pacemaker potential, the drift towards threshold occurs because of leakage sodium channels, and the sodium is supplemented with calcium from calcium voltage gates during depolarization. And then finally, the constant leakage of sodium makes this action potential slower than we would see because both the pacemaker's depolarization and repolarization phases take longer than they would take in skeletal muscle.